In this task, we're going to use a microwave oven and some chocolate to measure the speed of light because, well, why not? You'll need a plate, a big block of chocolate, and a microwave. Open the chocolate and place it upside down. This gives us a nice flat surface facing upwards. Remove the carousel plate and holder from the microwave. We don't want the chocolate to rotate while it's in there for reasons we'll get to later. Put the plate with the chocolate in the center of the microwave, ensuring that the chocolate is flat and level. In this microwave, I had to put a plastic cover over the thing that turns the carousel and place the plate on top of that. Our aim here is to heat the chocolate just long enough that we can start to see points on the surface where it's melting. It's really important not to heat it for too long and melt the whole thing, as it'll make it impossible to measure and probably make a huge mess of your microwave as well. So on high power, turn the microwave on in bursts of 10 seconds at a time. Depending on the power of the microwave and the starting temperature of the chocolate, it could take between 2 and 5 of these 10-second bursts. Each time, carefully check the chocolate for spots where there's a change of appearance. It starts to look a little bit soft, or you might see the chocolate sinking. There's one spot starting here, so I'll do one more burst to finish. So this is a good time to stop. You can see that there's 2 or 3 spots on the surface of the chocolate where melting has started. You've used the wave equation before to calculate wave speed, and the wave equation is speed is equal to wavelength times frequency. So we're going to use this equation again here to calculate the speed of light. So we need to determine the wavelength and frequency of the electromagnetic waves that the microwave is emitting. With a ruler, measure the distance between 2 of the spots. You might have a few spots and you can compare them to get a rough average. We'll take the shortest distance in this case, which is about 7 centimeters. Now, inside the oven, the waves actually bounce around, reflecting off the surfaces inside, and this forms what's called a standing wave. These standing waves look as if the wave is standing still. There are alternating points where there is a crest and trough, which are called antinodes, and points where there is no oscillation, which are called nodes. In the microwave oven, it's at the antinodes that all the energy of the waves is concentrated. To heat food evenly, microwaves have a motorized carousel that turns the food so that these points don't just hit one spot on the food. However, in our experiment, we wanted these points to hit one spot on the chocolate, so that's why we removed the carousel. The distance between 2 antinodes is actually half the wavelength of the wave. So our measurement of 7 centimeters is half of the wavelength of the waves the microwave emits. So we double that to get the full wavelength of 14 centimeters, or 0.14 meters. The other value we need is frequency. And thankfully this is a little bit easier. Either printed on the back of your microwave or in the specifications in the instruction manual, you'll see the frequency value. In this case, it's 2,450 megahertz, which is 2,450 million hertz. So for the speed calculation, we just have to multiply our wavelength, which was 0.14 meters, by our frequency, 2,450 million hertz, and this gives us a speed of 343 million meters per second. Now the documented speed of light is 299,792,458 meters per second, so our calculation is out by about 14%. But that's not too bad for chocolate in a microwave.